So I'm extremely happy to have been given this opportunity to express my gratitude to my teacher, Bernard. And we first met something like 45 years ago. And from the very beginning, Bernard transmitted me his enthusiasm and joy of doing mathematics. And I'm very grateful for his constant support and encouragement, and in fact for his most precious gift, which is freedom. And I can't resist quoting an epigraph of one of his papers. I mean, it's a Unza saying. I don't know if it's apocryph or not. And it's something like, better a house without a roof than a house without a view. Okay, so I have chosen the topic of the talk according to what I know of Bernard's taste. So I think words like valuations, polyhedra, I mean, they are supposed to be appropriate too. I plan to start, I mean, in the abstract, I promise to start with recalling Bieri groove theorem, but in fact, in view of short timing, I will not do it. As one say, if I have time enough at the end of the talk, which means, you know what. Okay, so I'll start by stating the main result of the talk. The point is that most of the words will not be understandable by the audience, but my point is to explain everything in the statement. So it's a joint work with Antoine Ducros, Hrushovski, and J, who is known under the first name of Vincent. Okay. So let K be algebraically closed. Ultrametric field. X be an algebraic variety, a K algebraic variety. Okay. So for the purpose of the talk, I have introduced names which you won't find in the literature, but okay. So good skeleton is just for the purpose of this talk. So to such a skeleton, I will explain what it is, of course. You can assign a group of so-called tropical functions. Then this group is tropically finitely generated over K. Here again, I mean, this terminology is specific to this talk. It's a pity that we did not use it in our paper, but okay. So that's the result I want to explain. I'm sorry? Okay, it's yes, but it's okay. I mean, yeah, but then there's no valuation here, so let's keep over K. Okay, so first, what is an intrametric field? So it's a field endowed with an intrametric norm. Satisfying the ultrametric inequality, which takes this form. Okay, strictly speaking, I will explain the identification, and strictly speaking, then K should be complete, but this will never, it's not used anywhere, so we don't have to assume it's complete. Okay, so now if I take X an algebraic variety over K, let me assume that X is affine. Okay, in fact, the statement is in fact birational. I mean, it's the same statement for any variety birational to X, so we could as well assume from the very start that X is affine. I won't do it, but anyhow, it's enough to explain the identification in the affine case. In the non-affine case, it's done. It's not complicated. It's deduced from the affine case by gluing. So in this case, the Xn is the so-called Berkovich identification. There are other variants, but this is the one. And it's the set of multiplicative. Okay. Compatible with an original norm on K. I guess this is clear enough. Semi-norm is just like a norm, but you don't have that. You can have a norm 0 and not be 0. And multiplicative means norm of x, y is equal to the product of the norms of x and y. Okay, so if I take a point in Xn, okay, it corresponds to a semi-norm, which I will denote by like this. So which goes from A to. Okay, and in the title, I'm speaking about valuations, and we will see valuations. So what's the connection with valuation? So I can view X as a valuation, or maybe better this. So this induces a norm on a field which I denote by K of X, which is a fraction field of A modulo the kernel of the norm, which is a set of elements of A for which the norm is 0. Okay? And so I have a norm on a field. This field is a finite type extension of K. And by taking minus the log of this norm, I can view it as a valuation. That's one thing. So this is a finite type of K. And so there is a classical condition, which of course is only known to people who are used to this field, which is called the Abyankar condition, which will play a role in this talk. So let me remind you what is Abyankar, what is an Abyankar valuation. So if I have an extension of valued field, finite type extension of valued field, we say that it is an Abyankar extension if the following equality is satisfied. So you take the transitional degree of the extension, and you have an induced extension of residue field. So let me write the residue field like that. Plus something coming from the value group, which I will denote by gamma, like in the talk of Arthur. So that's an Abyankar extension, and equivalently we could talk about Abyankar valuations. Okay, so in general there is only an inequality, so this is not smaller than this sum, and you have the Abyankar property when it's actually an equality. Okay. So it's not really needed for this talk, or it's kind of needed. Xn is not only a set, but a topological space. So you take the coarsest topologies, so the one with the smallest number of open sets, such that these maps are continuous. So it's kind of a product topology, yeah? So one should be careful because usually one sees nice pictures, and for instance, of the identification of a curve, and you see things on the plane. And a common misconception is that what you see pictured in the plane is endowed with the topology of the plane. It's not true. Okay? Now I will define what is a skeleton. So I will give a completely ad hoc definition of good skeleton, and at some point I will explain briefly that there is a conceptual definition. Okay? So I will start with the so-called standard skeleton. So GM is just the affine line minus a point. It's a spectrum of okay? And what is this S1? So is a set of seminorms. So I have to put a seminorm on this guy. And here is this is a definition. And so I have identified S1 with positive real numbers, but I prefer, okay. In this field, you have always a choice between norms and valuations. Norms are nice, but valuations are better because we will do some piecewise linear geometry, and I don't want this piecewise linear geometry to be, I want to use additions and not multiplication for piecewise geometry, otherwise I don't understand anything. And so we take the log. And now we can identify S1 with real numbers. And in fact, this identification is at the topological space. S1 is embedded in Xn, which is endowed with a certain topology. And one can check that this is a homeomorphism. And in some sense, which I don't want to make precise, S1 is really endowed with canonical linear structure. And this can be extended to higher dimension. Okay, instead of, in fact, these norms, they correspond to two subnorms on disks, closed disks. And instead of this, you can take polydisks. And so you get, I won't write the detail, but you have something like that. Okay. So, and it's also endowed with a linear structure. And so the idea is to build a more complicated subset of Xn. So here, X is only GM or product of GM, but for any X. And so the way is to, starting from an X, to map to some GM, to some power, to some torus, and to build out your skeleta by taking pullbacks of such things. So let's do this. So let X of dimension in fact, I prefer to assume X to be irreducible. Maybe one need it in the statement of the theorem. No, I don't think so, but okay. So roughly speaking, a skeleton inside Xn should be some subset endowed with a PL structure. Should be built out of linear pieces. Okay, so let me give a definition. So I take a finite number of functions from x to okay, this is not the same m, but okay. So what's important is x of dimension n, and here it's the same n. So these maps are generically finite. Okay, I don't have to write it, but each phi I is generically finite. Okay, that's very important. Okay, and so an identification is functorial. This is quite clear. So if I have a morphism, I have an induced morphism between the identification.
They are generically finite onto GMN or the image or on the image?
That's the same dimension.
Same dimension.
So it's very hard for, if you have two maps between irreducible varieties, between one map between, okay, you see what, you know what I want to say. Okay. So I take so each Sn should be considered as a linear space. And I take, so the pre-image is a linear space inside Xn. I take this union. And I want sigma to be inside. But I want, okay, this is, to be equal to that, it would be very, very restrictive. Huh? So I want sigma to be defined by linear inequalities. Between functions of the form so G is a non-zero rational function on X, which was assumed to be irreducible. And, or maybe I should put some an here. So I have to explain something very, 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 very important to understand what's here, is that this is completely birational notion. Why? Because the point of Sn, they are generic. They are not contained in any so let me write this down. This means that if X belongs to any the identification on any closed subvariety of X, then Y has to be X. Okay, you can also say it in terms of the transcendence degree of the corresponding field. Okay, so this is first. And it satisfies the Biancar condition. So this is why I call it this Coletta good, because they have specific properties. All their points are dense and are Biancar. And why is it so? It's very clear. It's obvious. It's enough to check that the points in Sn are generic and are Biancar, which is completely clear because the points are generic because they correspond to subnorms on closed disk of non-zero radius, so they are not concentrated at a closed point. The same for polydisks. And they are Biancar because they are Biancar, because you can check it. I mean. Okay, and then it's very easy to check that these preimages still consist of points having these properties, because phi's are generically birational. Okay, so now I have to define the tropical functions. And something, okay, something important is, in fact, for this to make really sense, one needs all the points to be dense. Because, for instance, if G would vanish or not be defined at a point, we would be in trouble. But since we consider only G at points which are dense, there is no such a problem. Okay, that's good. Now, what are the functions we are interested in? You will not be surprised if I consider the set of function. Yeah, I don't know if I should put an or not. I mean, the key is that this function can be extended. Maybe the an should be, I don't know. This function can be, the value of such a function can be given at any point. Of course, I mean, you take the value at a point. I mean, in the sense of the definition. Okay. So restricted to sigma, of course. Okay. So there are basic properties of this guy. So it's clearly a group, because Kx star is a multiplicative group. So this is an additive group. Less obvious is that it's stable under max and min. So we have a proof of this in our paper, which uses some basic model theory, but I've been told by Antoine Ducros that one of his students find a direct proof, and I think the student is here, maybe. You're here, okay. So you can confirm? Okay. That's it? So we still have to explain what this means. So there exists a finite number of elements of this group. Such that for every f is obtained from the GIs, but is relative to k, or valuation of k, as Amit said. So I have to add constant by using in other words, it's a word in plus, minus, min, max, the GIs, and some, of course, it's a finite word, so there will be only a finite number of constants showing up. Okay? So now we have explained the statement of a theorem. So before going towards the proof, let me just say that it's known by a counterexample due to Temkin that we need some hypothesis on the field. So we can only prove it when it's algebraically closed. Maybe there is a weaker hypothesis, but the example of Temkin is relatively bad in the sense that it's not a stable field, or defectless field, I mean. But I think I will go say a bit more later. Okay. So now I want to explain the main steps in the proof. What is maybe a bit surprising is that one of the big steps has nothing to do with valued field, is purely within the realm of piecewise linear geometry. So I guess that Arthur introduced the language of valued field. So you had the three source of variables, and so you have the gamma, which was correspond to the value group, and which was endowed only with plus, minus, and an order. Okay. And so let's do some PL geometry. So we take a gamma divisible ordered abelian group. And we take as language sorry. Okay. I will not talk about the constants in this talk. Okay. And what is a definable set? If only if D is a Boolean combinations of sets of the form so Q affine. This means of the form, and so these are the coordinates. The coefficient they lie in Q, and the constant lies in gamma. Because remember, in this setting, you don't have multiplication, which is good because you have less complicated objects, but sometimes it's embarrassing not to have multiplication. Okay. And now let me. I have to finish at 12:30. Is it? Yeah. So let me so the prologue I intended I will not I don't have time to do was the Bieri-Groove theorem. The Bieri-Groove theorem is a theorem saying that the image on certain maps of algebraic varieties or identifications are a combination of finite combination of polytopes, and it has been observed by Ducros that one can give a very direct and conceptual proof of this just using quantifier elimination in the three-source language, because basically it's not the proof is more complicated than one I will say, but basically if you have something in ICVF, you take its image in gamma to the power of something, it will be definable, but if you're definable in gamma n, you're just piecewise linear, and that's the end of it. Of course, there is more to do, but okay. So now I state a theorem, of course, by the same four guys, which is purely is okay. So I take D in gamma m. Definable, so this just means, as before, just a Boolean combination of sets defined by linear conditions, inequalities between linear conditions. I take a function which I assume to be Lipschitz. I will comment on this. And definable. So what means Lipschitz? So Lipschitz means, what does it mean? And what is this norm? It's just on gamma m. You of course you define a norm by taking. So this is additive. So to become multiplicative, you have to take some exponentials, and you do this coordinate by coordinates. It's the sup of norm of something on gamma to some power is the sup of the norm of the coordinates. Okay, so here it's just in gamma, but here it's okay. Take Q affine functions, or maybe it should be a different. Such that for every point in D, there is some I such that g of x is equal to the value of some of this guy. Then G is expressible as a term, as a word in the FI's coordinate functions and constants using plus max min. Of course, if you are a word involving a certain finite number of functions, you will have the weaker property because you can list a finite number of functions using you looking at your word. I mean, and the value at every point will, because for instance the max of two functions, I mean this value as a point is either one of the function or the other one. Okay. So this is not easy to prove, and it's really a piecewise linear statement. So the Lipschitz condition is fundamental, because let's take a stupid example in gamma 2. So here I take, so this is the axis, let's say. Here I take the function with value x, so let's say this is, I am at finite distance, so let's say this is, I have something called 1, say, which is not given, but is possible. And here I put 0. So this is clearly a definable function. But it's not Lipschitz, because the value can be very large. It's not compact. But I'm always quite close to something with value, to someone with value 0. And I can check that one has a first property, but not the conclusion. So we really have to do something. OK, so now I have something like 5 minutes. So it's time to go a bit faster. So the strategy is as follows. First, we replace x hat by x hat. So x hat is something I introduced with Hrushovski in a book, and it's a model theoretic variant of x hat, and it has some advantages, which it is pro-definable. It's not definable. It's not a definable set, but it's a projective limit of a definable set in some slightly bigger language than the one Arthur explained. And so I will not write it on the blackboard, but let me just say that now I can explain what is a skeleton in this framework. A skeleton inside x hat is just a definable subset, which is in pro-definably isomorphic to some definable subset of some gamma to the power m. So one can give a very neat and direct conclusion. And it's a fact that property of being good, so Doyen's points and Abyankar condition, in this framework is equivalent to the definition I gave. So that's one thing. OK, and first step, so I take some skeleton inside x hat. We should embed the skeleton in topologically in some gamma m. This we know how to do it, such that the first hypothesis holds. The hypothesis in the previous theorem holds. So let me call this also, okay, for some people. I don't have much time to be. And the key to the first step is, theorem by Franz Victor Kuhlmann. Is that, oh, there is some H, okay, some H missing. Biancar extensions of defectless fields are defectless. What is a defectless field? It's just it's a valued field such that every finite extension is defectless. Defectless means sigma of EI Fi equals n. Okay? Okay, by the way, in the paper we give a more model theoretic proof of Kuhlmann's result. But that's just a minor point. So this enables us to have, well. Now, to conclude, we need to have an embedding with the Lipschitz property to be deduced to have from the weak generation to have the strong generation we want. And that's the hard part of the okay. I'm sorry?
What does defectless mean?
Yeah, defectless means so K is defectless for every finite extension . Okay. Okay, I'm almost over my time. I just want to say that to prove the theorem, we have some nice convex geometry to do, and I think this would be, please, Bernard. We need some convexity. So it's a bit. Okay, it's not easy. It takes something like 10 pages to prove this, but okay, I think it's time to end this talk. Thank you.
Thank you for your talk. Are there any questions?
Can you please repeat what it means that the condition star holds? Can you repeat what it means that star holds for this embedding?
In fact, I think what I said, because of lack of time, I was not very precise. So let me say there are two kind of generations. One is what we call the piecewise or weak. This means you have a finite number of functions. And but this finite number of functions can be obtained for some as linear combination of certain generators. I mean, this I'm just skipping. And this weak condition just means that at a given point, the value of the function you want to prove that it's, so to speak, generated by the other ones, it's just one. You have at least one of these generators with the same values. And the stronger condition is that these are obtained as min-max.
Thank you. Other questions? If not, before thanking François again. Okay.